For thousands of years, people could only observe electricity from a distance. It flashed across the sky as lightning and appeared as tiny sparks when amber was rubbed with fur. Then, in 1800, Alessandro Volta invented the first practical battery, giving scientists, for the first time, a steady source of electric current. But there was little they could actually do with it. There were no electric lights, motors, or electronic devices waiting to be powered. So scientists began asking a more fundamental question. What can electricity actually do? 20 years later, Danish physicist Hans Christian Ørsted accidentally discovered the answer. A compass placed near a current-carrying wire suddenly changed direction. Electricity could create magnetism. That single observation forever changed our understanding of nature. Inspired by Ørsted's discovery, English chemist Michael Faraday became fascinated by the connection between electricity and magnetism. In 1821, he built the first device capable of producing continuous motion from electricity. A current-carrying wire was suspended beside a permanent magnet in a container of mercury, allowing it to move freely while maintaining electrical contact. When connected to a battery, current flowed through the wire, causing it to rotate continuously around the magnet. Rather than pulling the wire toward the magnetic field produced a force perpendicular to both the current and the magnetic field, causing the rotation. We now call this the Lorentz force. For years, he experimented with magnets, coils of wire, and batteries, but simply placing a magnet next to a wire produced no electricity. By then, scientists had developed the galvanometer, an instrument sensitive enough to detect even the smallest electric currents. Then, in 1831, after more than a decade of investigation, Faraday wound two coils around a large iron ring. One coil was connected to a battery, while the other was connected to a galvanometer. When he closed the switch, the galvanometer briefly deflected before returning to zero, even though current continued flowing through the first coil. When he opened the switch, the needle deflected again in the opposite direction. The experiment revealed something remarkable. A steady magnetic field does not generate electricity. Only a changing magnetic field does. To confirm the idea, Faraday repeated the experiment using a single coil and a permanent magnet. Moving the magnet into or out of the coil produced a current. Holding the magnet still produced nothing. The same result occurred if the coil moved instead of the magnet. It wasn't the magnet itself that mattered, but the relative motion between the magnetic field and the conductor. Looking back at Faraday's motor from the opposite perspective, we can also say that as the wire moves through a magnetic field, the field pushes the free electrons inside the conductor sideways, generating an electric current. So what determines how much electricity is generated? Move the magnet slowly through the coil and only a small voltage is produced. Move it faster and the voltage increases. Reverse the direction of motion and the current reverses as well. Now, replace the single loop with a coil containing many turns. Each turn generates its own voltage, and together they add up. This reveals one of the most important ideas behind every generator. It isn't simply the presence of a magnetic field that matters, but how quickly the magnetic field passing through the coil changes. We call the amount of magnetic field passing through the coil magnetic flux. The faster the magnetic flux changes, the greater the induced voltage. Now imagine rotating the coil continuously between the north and south poles of a magnet. As the coil rotates, its orientation relative to the magnetic field continuously changes. This causes the magnetic flux passing through the area enclosed by the coil to increase and decrease throughout each revolution. At the top and bottom of the rotation, the magnetic flux through the coil is at its maximum, but for an instant it is no longer increasing or decreasing. Since the magnetic flux is momentarily changing at a rate of 0, the induced voltage is also 0. As the coil rotates away from these positions, the magnetic flux begins changing more rapidly, causing the induced voltage to increase. At the left and right sides, the magnetic flux passing through the coil is 0, because the magnetic field runs parallel to the plane of the coil rather than through it. However, this is also where the magnetic flux is changing at the greatest rate, producing the maximum induced voltage. During the second half of the rotation, the magnetic flux reverses direction. The induced voltage reverses as well, causing the current to flow in the opposite direction. As the coil continues spinning, the voltage repeatedly changes polarity, producing what we call alternating current, or AC. If we plot this voltage over time, we obtain the familiar sine wave. It follows this shape because the magnetic flux through the coil changes smoothly as the coil rotates, and the induced voltage is proportional to the rate at which that magnetic flux changes. Let's look inside a portable generator. The engine provides the mechanical rotation, while the generator, also called an alternator, converts that motion into electricity. Inside are two main components: the rotor, which spins, and the stator, which remains stationary. Unlike our earlier example, modern generators usually don't use permanent magnets. Instead, the rotor contains a coil called the field winding. When supplied with a small DC current through two slip rings and carbon brushes, it becomes a powerful electromagnet. As the rotor spins, its magnetic field sweeps past the stator windings, continuously changing the magnetic flux and inducing an alternating voltage. You might wonder why the electromagnet rotates instead of the output winding. After all, either arrangement would generate electricity. The reason is that the stator carries the generator's full electrical output. Passing that large current through brushes would cause excessive wear, heating, and sparking. The rotor, however, only requires a small field current, making it much more practical to supply through slip rings. That's why modern generators keep the output winding stationary and rotate only the magnetic field. The stator winding may look complicated, but it follows exactly the same principle as our single rotating coil. It simply contains many coils distributed around the stator. As each magnetic pole passes by, every coil generates its own voltage. By connecting these coils together with the correct polarity, their voltages combine into a single, much larger AC output. But where does the rotor get the current needed to become an electromagnet? A small auxiliary winding supplies power to the automatic voltage regulator, or AVR. The AVR converts this AC into DC and feeds it to the rotor through the slip rings. The AVR also continuously regulates the generator's output voltage. If the voltage falls as more electrical load is connected, it increases the rotor's field current, strengthening the magnetic field. If the voltage rises, it reduces the field current. In this way, the generator maintains a nearly constant output voltage. This generator is self-excited. Even after it is switched off, the rotor retains a tiny amount of residual magnetism. As the engine begins turning, that weak magnetic field generates a small voltage in the stator. The AVR uses this voltage to strengthen the rotor's magnetic field, which produces an even higher voltage. Within moments, this positive feedback builds the generator to its normal operating voltage. Larger industrial generators often use a separate permanent magnet generator and an exciter generator, instead of relying on residual magnetism. Although the excitation system is different, the electricity is still produced by the same principle of electromagnetic induction. At first glance, it might seem that the generator should spin freely while producing electricity. That is only true when no load is connected. As soon as a load, such as an air conditioner or a power tool, is plugged in, current begins flowing through the stator windings. That current creates its own magnetic field, which opposes the rotor's magnetic field, making it harder to turn. The engine must now produce more torque to maintain the same speed. This is why the engine sound changes whenever a heavy electrical load is connected. The more electrical power we draw from the generator, the more mechanical power the engine must supply. A generator doesn't create energy, it simply converts the engine's mechanical energy into electrical energy. No matter how large or small the generator is, the same relationship always applies. Nearly 2 centuries ago, Michael Faraday discovered that a changing magnetic field could produce electricity. At the time, there were no electric lights, no household appliances, and no power grid. He had no idea how profoundly that discovery would reshape the world. Today, whether electricity comes from a gasoline generator, a wind turbine, a hydroelectric dam, or a nuclear power station, almost every watt is still generated using exactly the same principle. One of the most important discoveries in human history turned out to be surprisingly simple. Move a conductor through a changing magnetic field, and electricity is produced. Thank you for watching, and see you in the next video.